Assalamu alaikum wa rahmatullahi wa barakatuh. So today we are going to be starting the distributions, and the first distribution is binomial distributions. Well, technically the first distribution is probability distribution tables, but we have already done that under the topic of probability distribute under the topic of probability. So I think that would be enough. So you are going to be given a question, right? If it is a normal distribution, you won't have to figure it out. You're going to know it right away, right? You're going to know it right away. Is my sound even being recorded? Let me just like that. Yes, it is being recorded. Never mind. Now look. Now, the question that you're looking at, what will you have to figure out, right? You will have to figure out whether the question you're looking at is a geometric distribution. Why is that like this? The question you're looking at, is it a geometric distribution or a binomial distribution, right? This is what you will have to figure out on your own. If it's a normal distribution, right, then you're just going to know. I mean, identification for this is not that much of a problem. Identification would be a problem. It wouldn't be a problem. It would be for you to learn how to identify both of these, right? Because in the normal distribution question, they're always going to tell you, okay? I should have began by saying there are three types of distributions, normal distribution, binomial distributions, and geometric distribution. And from today, we are going to be beginning binomial distribution, okay? Now look, so Bismillah, we have already talked about the without replacement questions. Okay. Right? So remember one thing. Every time you see without replacement questions, these are never binomial. Not binomial, right? They can be anything. They can be, the Poseidon distribution. I think there is one in S2 or whatever it may be. It can be anything, but a without replacement question is never ever going to be a binomial distribution. That is one thing. Okay. Now, how do you know what is a binomial distribution? So the conditions for a binomial distributions or if you're looking at a question, how do you know it is a binomial distribution, right? The first thing would be that it would be a repeated experiment. Repeated experiment. Now look, a repeated experiment repeated a certain number of times. For example, I'm flipping a coin 10 times, flipping a coin 10 times, right? Or rolling a dice 20 times, right? So you see the first condition in here is being satisfied. You're flipping a coin, which means you're doing something. It is a repeated experiment and you're doing it a certain number of times. It's not like, okay, there's repetition. That's all we need. No, we need to know that it's a repetition and how many times is it being repeated? How many times how many times is it being repeated? The number of repetitions is something that you must know. Now, that was the first condition. The second condition is it would be discrete outcomes. Now, what do you mean by discrete? Sometimes the outcomes are infinite, right? Sometimes the outcomes are infinite. The example of this that I can give you is on any rainy day, how many raindrops are going to fall down? Now the outcomes are on a specific square meter area. Like let's say in my city, how many total raindrops can drop? What is the probability, right? So maybe one is going to drop, maybe two, maybe three, four, five, six. You don't know how many, right? These outcomes can be infinite, right? Or seemingly infinite. That these are not discrete outcomes, right? Or the outcomes must not be continuous, right? These should be discrete outcomes. Again, I'm going to give you the example of a coin or a dice. A dice has discrete outcomes. How come? When you roll a dice, there are a bunch of numbers and you can only get one number from the six sides or the four sides or the three sides depending upon how many sides does the dice have, right? So when you're flipping a coin, the outcomes are a head or a tail. These are the only outcomes, right? You can count them. You can just literally see how many outcomes are there, right? For let's say a six-sided fair dice, one, two, three, four, five, six, right? You won't have more outcomes than this. Let's say it's a 12-sided dice. Well, at least you know how many outcomes there are, right? That is what you call a discrete, or that is what you call discrete outcomes, right? This was the second condition. This was the second condition. Now, the third condition is, I should have made a circle around it. The success and failure thing. Okay. Now, what do I mean by success and failure? That is something which is not just, a part of binomial distributions. That is just what probability actually is. What do I mean by that? Every time we look at probability, we only are, dealing with two things. Either something happens or something doesn't happen. The very first class we had of probability, what did we learn? That probability is just a chance of something happening and something not happening, right? So something happening would be the success, and something not happening would be the failure, right? Yeah, the best part about statistics is that all of the topics are kind of intertwined with each other. They're interlinked, right? And like the concepts of one topic are always, or mostly, they are going to be used in some other parts, right? Or in an entirely new different kind of situation, but the concept is still the same, right? Now, instead of yapping, I'm sorry to use this word, but I would say this. Look, from success and failure, I mean that in this distribution or in this question, you are going to have the probability for a success, which you're going to denote with a P, and the probability of a failure, which you're going to denote with a Q, right? So, for example, let's say, uh, you know, Amanda is flipping a coin 5 times. What is the probability that, she obtains a head 2 times, right? Or she obtains a head 3 times? That is a binomial distribution. You know why? Because we know it's a repeated experiment and it's being repeated a certain number of times. I just said it's being repeated 5 times, right? And then, yes, there are discrete outcomes. It can either have a head or a tail, right? We know how many outcomes it has. We can count, the outcomes. Or in other words, the number of outcomes present can be counted. It's a valid integer. As for success and failure, I just said she may, you know, uh, get herself ahead, or she may not get herself ahead. So let's say, she's flipping a coin 5 times, right? And find the probability that she receives a head, 2 times in her 5 throws. She receives a head 2 times, right? Now, receiving a head, receiving or getting a head is the success in this case, right? Is a success in this case. And not receiving a head, not this entire thing, I'm not going to write it all over here again. Not receiving a head would be the failure, right? So we need to find the probability for both of them. The probability of getting a head for a coin is obviously going to be 1/2, right? Why? Because there are in total two outcomes. You can either have a head or a tail, right? And the favorable outcome is one. You've got only one head, right? Now, how do you find the failure? Once you have the success, you can easily find the failure. Remember one thing I told you. I said that the total probability is always going to be one. You know, the total probability is always going to be one. So, you know what Q is going to be? You know what the failure is going to be? 1 minus P. This is it. Literally. You just need to find the success, the probability of success, and you're literally getting yourself for free, you know, the probability of failure. You know why? Because the total probability is one. So if you know the success, then and you subtract it from 1, you get the remaining part, which would be the probability of the failure, right? So in this case, it would be q is equal to 1 minus 1 over 2, and that is also going to give you 1 over 2 in this case, right? That was just an example. This is what we mean by success and failure. It must have this concept of success and failure, okay? And now the fourth, last but not least condition for a binomial distribution is, for the fourth part is, sorry, P, Q, and N are constants. I'm going to end today's lecture on this, right? And then we're going to move on with the second one. Now look, P, Q, and N, which means the probability of success, the probability of failure, and the total number of outcomes, they're all constants. Meaning, let's say, Amanda is flipping the coin 10 times, like we said over here, right? She flips the coin once, and you get yourself the probability for P, Q, and you already know N, and it's 10 in that case, right? And she flips it again, and she flips it again, and she flips it again, right? Every time she flips the coin, the value for P, Q, and N does not change. This is one thing you need to remember. you know so if you see a question, and that looks like, it seems like, apparently what you're looking at is a binomial distribution, you know in that case, the first condition is being satisfied, the second condition is being satisfied, and also you find yourself the concept for a success and failure inside that question as well. You're like, aha, found it. Or this must be a binomial distribution. But look, hold your horses. Remember to take a look at this. The fourth condition. If P, Q, and N are not constant, you can never ever have it as a binomial distribution, right? And look, what did I say at the very beginning of the lecture? Without replacement questions can never be binomial. They can never be binomial. You know why? This is why without replacement questions can never be binomial. This is the reason. Now, let's look at why is that the case. Why is that the case? Look, I've got myself this bag, right? And I've got, let's say 10 squares, 3 squares and 3 balls, right? 4 balls, let's say, right? And Amanda is picking up one after the other 2 balls, or, 2 things from this bag, right? What is the probability of her picking up a square? Or what is the probability of her picking up 2 squares, right? Without replacement. She's not replacing them. So let's say the probability of her picking up 2 squares, outright S and S, right? Probability of picking up 2 squares. The probability of picking up for the first square would be 3 over 7, right? Remember, without replacement. So once she picks up something or anything, she's not going to put it back in the bag, right? Now look, the probability of picking up both squares would be 3 over 7, 1, 2, 3, 4, 5, 6, and yes, multiplied by, now notice something. She didn't put that square back in the bag, right? So it must turn into 2, right? And the total outcomes would be 6. Now this is both of these are probabilities of success. Both of these are P's, right? But are they constant? No, they're not. They got changed, right? This is why we say that without replacement questions can never be can never be binomial distribution. Remember this one thing. That was all for today's lecture. From tomorrow onwards, inshallah ta'ala, we're going to be focusing more on, the formula for this. Right? I mean, I can tell you the formula right now, but it would take some time to explain that, right? And you're going to understand it much better once we start with combinations and permutations. We're also going to do a couple of questions, for binomial distributions, and that's it for today's lecture. Assalamu alaikum warahmatullahi wabarakatuh.